You are on a mountain road in China. Cliffs on your left, a drop of 300 meters on your right. No guardrail, no room to pass. And the road, if you can call it that, is carved directly into the vertical rock face by villagers using hand tools over 8 years. That route exists right now. People drive it today, not because they have to, because they chose to build it there instead of asking anyone for permission or funding or a safety inspection. These are not legends. These are construction projects with documented engineering records, built by humans who decided that impossible was a description of where they started, not where they finished. Today, we went through every single one. By the end of this, you will look at every structure you pass and wonder what it took to make it stand. Let's go. The Dancing House in Prague is a personal attack on every one of those principles. Designed by Frank Gehry and completed in 1996, the building looks like two figures mid-dance, one rigid, one fluid, frozen in concrete and glass on a Prague street corner. That flowing, curving female tower required 99 individually cast concrete panels. Not 99 similar panels, 99 completely unique ones. Each required its own geometry calculation, its own mold, its own structural analysis. Then Gehry went further. The window frames across the curved facade are not vertical. They are intentionally tilted at angles, creating the visual effect of fabric twisting in wind. For every non-standard opening, the structural team had to recalculate load paths from scratch. The building does not move, but standing underneath it, looking up at those cascading glass panels and those tilted windows and that impossible waste, you feel it move anyway. That is what happens when architecture stops following rules and starts making its own. Please hit like and subscribe because it really motivates us to reach more people through this video. Millau Viaduct in France is taller than the Eiffel Tower, not close to it, 19 meters taller. The Millau Viaduct in southern France reaches 343 meters at its highest structural point. Drivers crossing it in low cloud conditions report seeing aircraft beneath them. The bridge opened in December 2004 and held the record as the tallest bridge on Earth for over 2 decades. But the construction method is what stops engineers mid-sentence when they describe it. Yes, the valley is too deep for conventional building from the ground up. So teams at both ends assembled the complete steel deck on flat ground, then used a synchronized hydraulic jack system to push the sections out over the valley simultaneously, 60 centimeters at a time, across a drop of hundreds of meters. If either advancing section moved fractionally faster than the other, if the synchronization slipped once, the unsupported deck would twist under its own weight and fall. They pushed. It held. 7 slender pylons now carry a roadway above the clouds. People call it the most beautiful bridge ever built. Beautiful was not the plan. Not falling was the plan. Beauty was the result. SUMELA Monastery in Turkey, where not everything on this list is made from steel and concrete. Some of the most insane constructions were made from rope, faith, and refusal to accept that vertical rock is not a building site. SUMELA Monastery is embedded into a sheer cliff face in Turkey's Pontic Mountains at 1,200 meters above sea level, not built beside the mountain, but carved directly into it. Founded in 386 AD, the complex was cut by hand into living rock using tools that would embarrass a modern hardware store. Workers built on vertical surfaces with no safety systems recognizable today. Frescoes painted on those cliff-cut walls over 1,600 years ago still survive. Rain, earthquake, and centuries of abandonment have damaged them but not erased them. Supplies reach the site via rope systems and mule paths that challenge experienced hikers today. So every piece of material was either carried up by hand or quarried from the cliff itself. SUMELA operated as an active monastery for over 1,000 years before being abandoned in 1923. The mountain did not give it back easily. It took 14 centuries of continuous human presence to carve what you see. The cliff barely noticed. Leaning Tower of Pisa. Here is a building that became the most visited structure in Italy because of a mistake. Construction began in 1173 on soft riverbed soil, a mixture of clay, mud, and sand that 12th century engineers clearly did not test thoroughly enough. By the third floor, the tower was already visibly sinking on one side. Any rational project manager today halts work, files reports, and demolishes the whole thing. The Italians decided to keep building. For 177 more years. The completed tower weighs 14,500 tons and leans at an angle that by the 1990s had reached nearly 5.5 degrees from vertical. Close enough to critical failure that engineers calculated perhaps 50 years before collapse. Emergency stabilization work between 1993 and 2001 brought it back to 3.97 degrees. Not corrected, just stabilized, because a straight Tower of Pisa is just a tower. Nobody travels to Tuscany for that. The soft soil that caused the lean also absorbed the pressure that would have cracked a rigid foundation. The floor preserved the structure. The mistake became the monument. Sometimes the universe rewards the stubborn. Yusufeli Dam in northeastern Turkey, and the Çorum River cuts through one of the deepest gorges in the country. A canyon so steep and so narrow that before any construction could begin, engineers had to blast entirely new access tunnels through the surrounding mountains just to get their equipment to the site. There were no roads, there was no flat ground. There was a raging river at the bottom of a vertical gorge and a set of instructions to build the tallest dam in Turkey's history. Yusufeli Dam stands 275 meters tall, nearly the height of a 90-story building, plugging that gorge with a wall of concrete that holds back a reservoir large enough to have swallowed an entire town. The historic settlement of Yusufeli, a real community with real history, was fully relocated before the first pour. 15,000 people moved so this wall could exist. I standing at the base and tilting your head back, looking up 275 meters of concrete, while the sound of the contained river pushes through the structure around you. You understand something on a physical level that photographs cannot communicate. What is being held back is not water, it is force. The Wulong Karst Geological Park in Chongqing, China, is what 300 million years of rainfall, dissolution, and geological pressure looks like when it runs uninterrupted. Limestone formations so ancient they predate the dinosaurs, now standing in shapes so extreme that filmmakers use them for alien planets and fantasy worlds because CGI cannot match the reality. 3 natural bridges span the valley in sequence, the longest stretching 354 meters with a clearance height of 150 meters beneath the arch. And a 50-story building fits under that gap with room to spare. Sinkholes here drop over 600 meters into the earth, wide enough to develop their own internal weather. Clouds form inside them. The Qingkou-Tianqing sinkhole holds a separate valley ecosystem inside its vertical walls, a world within a hole, sealed from the surface, running its own biology in isolation. Film crews have used Wulong for Transformers and multiple major productions, not because they needed effects. They used it because nothing they could render looked this real. 300 million years built what no human budget could replicate. The Great Pyramid of Giza in Egypt, where 2.3 million stone blocks, each one weighing an average of 2.5 to 3 tons. Some of the interior granite blocks reaching 80 tons each, and total weight of the structure, approximately 6 million tons, heavier than every aircraft carrier currently active across every navy on Earth combined. Built in roughly 20 years, 4,500 years ago, with no steel, no concrete, no cranes, no computers, and no combustion engine of any kind. What they had was bronze tools, wooden sledges, rope, sand used as a friction-reducing lubricant under moving sleds, and a logistics organization sophisticated enough to feed and rotate a workforce of tens of thousands across 2 straight decades. Modern engineers who study the interior report 2 things consistently. First, the precision is not what they expected. The base is level to within 2.1 centimeters across 230 meters. In 2500 BC, without laser levels. A second, the blocks fit together so tightly that no mortar was needed and a sheet of paper cannot be inserted between them. The Great Pyramid does not just exceed ancient expectations, it exceeds modern construction tolerances. That is not a metaphor. That is a measurement. Umpherston Sinkhole in Australia, where it exposes a 24-meter-deep underground chamber to open sky. Most governments fence it off with warning signs and a parking fee. The people of Mount Gambier, Australia, decided to build a garden inside it. Since the 1880s, the Umpherston Sinkhole has been terraced, planted, and maintained as a sunken garden descending into the earth. Hanging plants spill down the sheer limestone walls, Native species root into cliff face crevices where no viable soil exists by any conventional measurement. After dark, possums descend from the surrounding bush in numbers large enough to make the garden walls appear to move. What makes this extraordinary is what exists beneath it. The Umpherston Sinkhole connects to an underground cave network running beneath the entire Mount Gambier region. A honeycomb of dissolved limestone passages linking to Blue Lake, the town's drinking water supply, which sits in another collapsed cave system nearby. The entire city is built over hollow ground. Ancient waterways and collapsed chambers run beneath every road and building. The sinkhole is just the place where the ceiling gave way first, and someone looked down, shrugged, and planted hydrangeas. The Great Wall of China is 21,000 kilometers. Well, not a wall in any sense that a builder today would comfortably put their name on. A dragon. A stone dragon that coils across the most punishing terrain in Asia, over mountain ridges, through desert passes, along cliffside routes where both sides of the path drop away, and only the wall gives you something to hold. Built across 2,000 years by multiple dynasties with different enemies and different resources. Workers on the mountain sections had no supply chain in any modern sense. Every brick that went into those high ridgeline sections was either quarried from the mountain it was climbing or carried up by hand. Historical records describe human chains passing bricks across cliff faces too narrow for pack animals, and mortared with a compound now known to include sticky rice flour. A binder so chemically effective that modern testing finds it still actively resisting moisture intrusion. The wall was never impenetrable. Mongols breached it by bribing gate commanders. Its real function was more complex. A communications network, a customs system, a supply corridor, and a statement of civilization that any approaching army could read from miles away. No modern project manager would approve the brief. The Chinese built it over 20 centuries anyway. If your brain is doing that thing right now, where you are already calculating which of these you need to see in person, this is the channel for you. Subscribe if you haven't. Share this with the person who needs to watch it right now. And keep going. Because the second half of this list is where things get truly unhinged. Palm Jumeirah and the World Islands. If someone looked at Dubai's coastline and decided there was not enough of it, so they made more. 7 billion cubic meters of sand and rock dredged from the floor of the Arabian Gulf and deposited with enough precision, guided by military-grade GPS navigation on every single sand-dumping vessel, to create a palm tree shape readable from orbit. Not approximately palm-shaped, exactly. Each frond positioned to specification before the first foundation pile was driven into it. The engineering problem was fundamental. Sand is not stable. An island of loose sand wants to become seabed again at the first opportunity. No engineers solved this with vibrocompaction, industrial vibration driven through the deposited columns until the granular particles lock under compression and behave like consolidated ground rather than a pile of beach. Then they went further. The world islands, 300 separate artificial landmasses arranged to form a recognizable world map, sitting in water that was 11 meters deep 25 years ago. Some remain undeveloped. All of them exist. Dubai did not expand into available space. It manufactured new geography and sold it. In Dubai, there is Burj Khalifa, 828 meters, the tallest building on Earth. But the height is not the story. The story is the shape. And why the shape was the only way this building could exist at those heights without shaking itself apart. In every skyscraper above a certain height faces the same enemy, vortex shedding. Wind hits a tall structure, spirals around it, and if those spiraling columns of air synchronize with the building's natural frequency, the structure begins to oscillate. It resonates, and resonance at 828 meters is not a vibration you feel underfoot. It is a structural failure, working in slow motion. The Burj Khalifa's design answer was a hexagonal central core, surrounded by 3 Y-shaped buttressed wings, each one stepping back at a different height as the tower rises, never simultaneously, always staggered. The staggered setbacks break the vortex-shedding pattern before it can synchronize. The building continuously disrupts the wind's attempt to find a rhythm. At the tower's peak, wind speeds during storms are 3 to 4 times those at street level. Oh, the building experiences this every day. It does not move. It was designed not to move. That is not fortune. That is physics, controlled with precision that required every material science advance available in 2010. Louvre Abu Dhabi, the problem. Build a world-class museum in one of the hottest environments on Earth, where summer temperatures exceed 50 degrees Celsius, that feels open, naturally lit, and cool without becoming an oven. Architect Jean Nouvel's solution was a dome, but not a dome that covers anything in any conventional sense. A lattice structure 180 meters in diameter, built from 7,850 individual geometric elements arranged in 8 interlocking layers. Each layer rotated slightly from the one below, each of the pattern derived from traditional Islamic architectural screenwork that has been creating shade in desert climates for over 1,000 years. The dome appears to float above the building complex on 4 concealed supports. The 4 pillars are deliberately designed to be invisible from almost every standard viewing angle. At specific times of day, sunlight penetrating through thousands of precisely calculated gaps in the lattice creates what architects call a rain of light. Thousands of individual beams appearing simultaneously on interior surfaces, shifting position as the Earth moves. Every gap was calculated, every beam was planned. The dome is simultaneously structure, climate system, and light installation, all 3 achieved by one ancient geometric pattern made enormous. Old intelligence, new scale. In Golden Gate Bridge, USA, before the first cable was spun, the engineers were told this bridge could not be built, not by competitors, by other engineers, by people who had spent careers building bridges, and understood what the Golden Gate Strait actually was: a channel where Pacific Ocean currents hit tidal flows at speeds capable of capsizing working vessels, where fog reduces visibility to zero for significant portions of the year, where the bedrock under the South Tower sits in an active seismic zone, where the required span, over 1,200 meters, had never been attempted. Construction began in 1933 anyway. The main cables required 27,572 individual steel wires per cable. This spun back and forth between anchorages using a continuous loop system, one wire at a time, until each cable contained nearly 130,000 kilometers of total wire. The cables reach 92 centimeters in diameter. They carry the deck 67 meters above the water. Workers operated in zero visibility fog at 200 meters of height in crosswinds. 11 died. 19 survived falls because Joseph Strauss hung safety nets beneath the deck, a first in bridge construction. The survivors called themselves the Halfway to Hell Club. The bridge opened in May 1937. 200,000 people walked across it on opening day, testing essentially whether it held. It was held. Erzurum Castle. In Turkey, most castles were built to stop armies. Erzurum Castle was built to stop everything. Situated on a high plateau in northeastern Turkey at 1,850 meters above sea level, the castle has been fought over, seized, and rebuilt by Romans, Byzantines, Arabs, Seljuks, Mongols, Ottomans, and Russians across 15 consecutive centuries. Each occupying force added their own layer. Byzantine stonework sits beneath Seljuk additions. Ottoman minarets rise from Byzantine foundations. The result reads less like a building and more like a geological record of every empire that ever wanted to control this corner of the world. The dark basalt construction material absorbs winter light and radiates almost none back, giving the castle a visual weight that makes it appear to belong to the mountain rather than to human hands. Erzurum regularly reaches -30 Celsius in winter. The walls were designed thick enough to maintain livable interior temperatures through stone mass alone. No heating system, no insulation, just physics. 15 centuries, multiple conquests, -30-degree winters, seismic activity. The castle is still standing, still solid, watching the plateau around it with the patience of something that has already outlasted everything that tried to take it down. Sagrada Familia. In Barcelona, Antoni Gaudí did not own a computer. He did not need one. He built his own structural analysis system from ropes, sandbags, and mirrors. Weighted ropes hung from a ceiling find the most efficient curve under gravity automatically, a catenary arch, which inverted becomes the ideal compression arch for a stone ceiling. Gordie loaded his rope model with sandbags proportional to the real structural loads, photographed the curves in mirrors placed below, then built upward from those shapes. The physics cannot lie. Gravity will always find the most efficient path. Gordie's rope model was computing what modern software now confirms. the structurally optimal form for every arch in the building, derived without a single mathematical equation. The Sagrada Familia broke ground in 1882. It is still under construction today, currently the answer to our opening engagement question, projecting completion around 2026, over 140 years after the first stone. The workshop models were destroyed in the Spanish Civil War. Decades of forensic reconstruction were required to understand what Gaudí intended. Modern engineering teams spent years digitally recovering what his ropes and sandbags produced in an afternoon. Both methods reached the same geometry. That is either humbling or extraordinary, probably both. Hoover Dam in USA. If you poured every cubic meter of concrete in the Hoover Dam into a single solid block, and then simply waited for it to cure, the heat generated by the chemical reaction would take 125 years to fully escape. That is not an analogy. That is thermodynamics. Concrete cures through hydration, a chemical reaction that generates significant heat. In a mass the size of the Hoover Dam, that heat has nowhere to go. The internal temperature would rise, the concrete would expand and contract unevenly, as in cracks would propagate through the entire structure, compromising a dam holding back one of the largest reservoirs in America. The engineers embedded 582 miles of steel tubing, 1 inch in diameter, throughout the entire pour. Cold water from a dedicated ice plant was continuously circulated through those tubes during curing, pulling heat from the interior outward. Each poured section took 2 months to cool instead of a projected 125 years, built during the Great Depression. Workers paid $4 a day. Desert Canyon, 110-degree summers. The dam still generates over 4 billion kilowatt-hours annually from concrete poured in the 1930s. That is not maintenance. That is original construction still performing at full specification nearly a century later. The Interlace, which Singapore has been stacking people upward for decades. Towers of identical floors, repeated until the skyline becomes a pattern rather than a place. The Interlace looked at that pattern and rotated 90 degrees. 31 apartment blocks, each one 6 stories tall, each one 70 meters long. Standard components assembled in a completely non-standard way. Instead of rising vertically, each block was rotated 120 degrees from its neighbors and stacked diagonally across the ones below, creating a 3-dimensional interlocking lattice across a wide ground footprint. 8 sky gardens emerged from the geometry, not added as amenity features, but structurally inevitable consequences of the overlapping arrangement. The gaps between crossing blocks create natural ventilation corridors that move air through the development continuously. The complex sits measurably cooler than surrounding high-density residential areas in the same humid Singapore climate. Every apartment has corner exposures in multiple directions. Views most Singapore high-rises cannot offer from a single floor. In a city where one good window view is a premium, the Interlace delivers several per unit as a direct result of the geometry. Changing the direction of the building changed everything the building could offer. Sometimes the innovation is not the material, it is the angle. Marina Bay Sands is the most recognized skyline element in Southeast Asia. 3 55-story towers, connected at their summits by a 340-meter cantilevered platform called the Sky Park, has extended 67 meters beyond the edge of the northernmost tower in open air, with nothing underneath that extension but the street below. That 67-meter overhang exerts a bending moment on its connection point that, without engineering intervention, would fracture the joint and drop the platform onto the city. The solution was post-tensioned steel tendons running the length of the Sky Park deck, giant pre-stressed cables counteracting the gravitational pull on the cantilevered end at the precise force required. The 3 towers themselves lean slightly inward at their tops, each one a different geometry converging on the same elevated connection point. The infinity pool at the Sky Park's north end holds 1.5 million liters of water at 200 meters of elevation. The plumbing system maintaining that pool, managing thermal expansion, the wind load on the water surface, structural flex in the deck beneath it, was developed specifically for this one installation. No existing solution existed. Marina Bay Sands opened in 2010 and immediately became the single image most associated with modern Singapore internationally. Not planned, inevitable. Veluwemeer Aqueduct in Netherlands. We started here. Now let's understand what actually happened. The Dutch faced a problem. A busy road and a busy waterway needed to cross each other in the Netherlands, and neither traffic system could afford to stop and wait for the other. A conventional bridge would require one to yield. A tunnel would be expensive and disruptive. The Dutch decided neither was acceptable. So they built the road underneath and ran the boats over the top. Our 22,000 cubic meters of concrete poured into an elevated water channel 19 meters wide, carried on steel piles above the highway. Boats cross, cars pass beneath. No traffic signal coordinates them because no coordination is required. 2 entirely separate systems, occupying the same physical location at different elevations, operating simultaneously without interaction. The project cost less than a conventional bridge solution. It solved both problems completely rather than compromising either. It required no ongoing traffic management, and it produced one of the most disorienting visual experiences available to any driver in Europe. The moment you glance up from a highway and watch a yacht sail over your car. When intelligent people solve problems, the results look obvious afterward. That is the highest possible compliment in engineering. Gordie Howe International Bridge. This is the answer to our opening question. 2 countries, 2 construction teams, 2 separate regulatory frameworks, 2 currencies, 2 sets of labor law, 1 bridge that had to meet precisely in the middle of an international river. The Gordie Howe International Bridge spans the Detroit River, connecting Windsor, Ontario, to Detroit, Michigan. International maritime law prohibited support columns in the water, making it the longest cable-stayed span in North America by necessity, not ambition. Both towers were built simultaneously from their respective national shores. Both halves of the deck extended outward day by day. The gap between them narrowed across 1,100 meters of cable-stayed construction. But when the closure moment arrived, engineers discovered the gap between the two halves measured 15 centimeters too narrow. 15 centimeters, after building 550 meters of bridge on each side of an international border. The solution, hydraulic jacks applied to the Canadian anchorage system, physically shifting the entire Canadian structure laterally, had never been attempted at this scale. Engineers developed, calculated, and executed it in the field during the closure operation itself. The joint closed. The bridge connected. Today, it carries thousands of commercial vehicles daily and has reduced cross-border freight bottlenecks by 35%. The 15-centimeter problem is a footnote. The bridge is the headline. Delta Works in Netherlands. On the night of January 31st, 1953, and the North Sea killed 1,836 people in the Netherlands. A perfect storm aligned extreme tidal conditions with severe, sustained winds. Dikes breached across the southwestern coastline. Water rushed inland. Entire communities submerged overnight with no warning and no escape. The Dutch response was not repair. It was transformation. Delta Works is a 43-year construction program comprising dams, sluices, locks, and movable surge barriers that collectively shortened the exposed Dutch coastline from 700 kilometers to 80. Not protected, shortened. The problem was not solved by building higher walls. It was solved by removing the coastline that needed walls. The centerpiece, the Meeslankering, is two hinged steel barriers, each as long as the Eiffel Tower is tall, floating in holding docks on opposite banks of the Nieuwe Waterweg Channel. When storm surge reaches critical thresholds, a fully automated computer system requiring zero human authorization swings both barriers into the river simultaneously. The system has operated since 1997. It has closed twice, both times without incident. 0 deaths from coastal flooding in the Netherlands since Delta Works' completion. That is not a statistic. That is a promise made to 1,836 dead and kept. Zeelandbrug Bridge, 5,022 meters. The longest bridge in the Netherlands and one of the longest in Europe. But the number that matters is not the length. It is the water underneath. The Zeelandbrug crosses the Eastern Scheldt estuary in the Dutch province of Zeeland, a body of water where the North Sea meets a major river delta, and tidal forces produce one of the most powerful current regimes on the European coast. Water reverses direction completely 4 times every 24 hours. At peak tidal flow, current speeds reach levels that actively push large vessels off course despite full engine power. Precast concrete pier sections were manufactured onshore and positioned by specialized vessels working within the brief slackwater windows between tidal reversals. The narrow periods when currents dropped low enough for precision positioning to be possible. If an operation ran over schedule, The tide simply took the section wherever it wanted. The bridge rests on 52 piers, each foundation established in those windows and against that current, with teams synchronized to tide tables rather than work schedules. The Zeelandbrug was completed in 1965, ahead of schedule, connecting isolated island communities that previously required full ferry crossings. The tidal forces that made construction nearly impossible now pass beneath it without acknowledgement, 4 times a day, every day, as they always have. The Gateway Arch is not a semicircle. If you have spent your life assuming it was, the arch has been quietly deceiving you and doing an excellent job of it. It is a weighted catenary curve, a specific mathematical relationship that flattens the arch slightly compared to a pure catenary, softening the apex so the structure reads as welcoming rather than sharp. Eero Saarinen chose this shape for 2 reasons. Visually, it looks right in a way that geometry alone cannot fully explain. Structurally, a true catenary carries load in pure compression, no bending moment anywhere in the curve, no internal framing needed, the structure holding itself up by geometry alone. Construction of the 2 legs proceeded from opposite foundations simultaneously, each rising 630 feet inward toward a meeting point that existed only on paper. On the day before closure, in October 1965, engineers discovered the gap between the 2 legs was 8.5 feet too narrow. The St. Louis sun had heated the steel, expanding it outward. Hydraulic jacks were used to force the legs apart. The keystone segment was dropped into place. Inside the arch runs a tram system designed solely for this structure. Barrel-shaped capsules that rotate on internal gimbals as the tunnel angle changes from vertical to horizontal, designed in the 1960s, still operating, still working perfectly. Akashi Kaikyo Bridge. For 24 years, this was the longest suspension bridge span on Earth. The gap between its 2 towers is 1,991 meters. Nearly 2 kilometers of open water. Drivers take approximately 90 seconds to cross that span with nothing beneath them but the Akashi Strait. The towers themselves reach 298 meters. On a clear day from the bridge deck, the curvature of the Earth is visible. Each cable anchorage block contains 350,000 tons of concrete, a mass comparable to a large naval vessel. Because the tension forces in the main cables under full traffic load would otherwise extract the anchors directly from the seabed. Each main cable is 1.12 meters in diameter, composed of 36,830 individual high-tensile steel wires wound into 290 strands. The steel specification was developed exclusively for this bridge. Standard cable steel was not strong enough. During foundation construction, the Great Hanshin earthquake struck in January 1995, magnitude 6.9. The quake shifted the 2 tower foundations approximately 1 meter relative to each other. Engineers resurveyed, recalculated, adjusted the cable specifications for the new geometry. Construction continued. The bridge opened in 1998. The earthquake that tried to stop it appears in the construction record as an adjustment note, not a crisis. Singapore Port. One ship arrives or departs every 2 to 3 minutes. Not one per hour, not one per shift, one every 2 to 3 minutes. Around the clock, 365 days a year, through night, through monsoon season, through the competing traffic of one of the most congested maritime straits on the planet. The Port of Singapore handles over 600 million tons of cargo annually, connecting 600 ports across 120 countries. More than 130,000 vessel calls are recorded each year. The port stretches 15.5 kilometers of active quayside, long enough to walk the entire coastline of Monaco 5 times without retracing a step. The logistics operation running beneath the visible surface is staggering. Automated stacking cranes operating on fixed rails move containers 24 hours a day with minimal human oversight. Software systems track the location, contents, destination, and handling requirements of millions of individual units simultaneously across a physical area the size of a small city. Singapore has no natural resources. No oil, no arable land to speak of, no industrial raw materials. What it has is position. The narrowest navigable point of the Strait of Malacca, the single most strategically critical maritime choke point in Asia. Singapore turned that geographic fact into the second busiest container port on Earth. Position is not a resource, unless you decide it is. The Kurushima Kaikyo Strait in Japan's Seto Inland Sea is not famous for a bridge. It is famous for 1,000 years of shipwrecks. 3 narrow channels converge between a series of small islands, creating tidal conditions that hydrologists still use as textbook examples of chaotic fluid behavior. At peak flow, currents reach 10 knots, enough force to push a fully powered vessel off its intended course despite maximum engine output. The direction reverses completely 4 times every single day. Japanese maritime records going back centuries document the strait as one of the most feared passages in the region. The Mori clan, feudal lords controlling this coastline, maintained a corps of specialist pilots whose only profession was navigating Kurushima. That knowledge was passed parent to child, and generation to generation, as a closely held trade secret. Outsiders did not pilot these waters. Outsiders who tried often did not come back. The Kurushima Kaikyo Bridge, actually 3 separate suspension bridges spanning the 3 channels in sequence, opened in 1999 as part of the Nishiseto Expressway. The crossing takes minutes. Today, tourists take boat tours, timed to tidal change specifically to watch the eddies and standing waves that ended maritime careers for 10 centuries. The bridge is above. The terror is below. The traffic moves between them and notices neither. We started with a boat floating over a car. We ended at a bridge spanning water that killed sailors for 1,000 years, crossed today in under 5 minutes by people checking their phones. Years between those 2 points, 26 structures. A pyramid that outperforms modern construction tolerances. A bridge closure fixed by a technique invented in real time over an international river. A monastery carved by hand into a cliff face 14 centuries ago. A dam so heavy it moved the Earth's axis. Not one of these was inevitable. Every single one required someone, an engineer, an architect, a builder, a ruler, a monk with ropes and hand tools, to look at what was being proposed and decide that impossibility was a starting point, not a conclusion. The Hoover Dam workers were paid $4 a day in a Depression-era desert canyon. The Great Wall brick carriers worked cliff faces with no safety equipment. Gordie's rope model decoded structural physics that took modern software decades to reconstruct. Are the buildings you walk past every day, the bridges you cross without slowing down, the ports that move your goods across the planet. All of it began as something that did not exist, that someone decided should, and then made real anyway. That is the entire history of construction, the entire history of human ambition, compressed into concrete and steel and rope and stone. If this video did that thing to you, the thing where you need to tell someone immediately, do us a favor right now. Hit like. 1 second. It matters more than you think for helping this channel reach people who need to see this. Subscribe and turn on notifications, because next time we go even deeper, the engineering failures that became the reason the successes were built differently, the disasters that changed everything that came after them. And leave a comment. And tell us which of these 26 genuinely stopped you. Tell us the one you are booking a flight to see. Tell us the one you would have refused to build. The best part of making these videos is reading those comments. We will see you in the next one.